Bessiere. She's a PhD student at the University of Sheffield. She's doing the PhD supervised by Clive Hunter, and I used to work with her, and I still continue doing that on the triggering mechanisms of powerful AGNs such as radio galaxies or quasars. And today she's going to present the work that she has been doing during the first year of her PhD. She has recently submitted a paper to Monthly Notices, and Patricia, so...
Well, hello, and thank you for inviting me here to the IAC to present my findings. As Christine said, my name's Patricia Bessiere, and I'm a PhD student. So over the next half an hour, I want to talk about the work that we've been doing at the University of Sheffield on whether powerful AGN are triggered in mergers, galaxy mergers and interactions. The work was begun by Christina, who analysed a sample of powerful radio galaxies to determine their interaction status and the rate of disturbance found in those. Now, I pretty much followed on from what Christina's done, but instead of using a sample of galaxies selected for their radio power, I've been using a sample of galaxies that's been selected for its optical power. So these are some of the most powerful optical galaxies in the universe. So anyway, what I want to do is present the results of the rates of disturbance that we found in that sample, and also compare it with the rate of disturbance Christina found for the radio galaxies, and also, importantly, a comparison with a sample of quiescent elliptical galaxies to see how the rates of disturbance between all the different samples stack up. So the first thing to do when you're talking about comparing samples of AGN is to define what you actually mean, because there's such a huge range of luminosities in AGN, ranging from liners at the very low end up to quasars and powerful radio galaxies at the top end. And there's no hard and fast rules about where you draw those boundaries between different samples. But a typical cut between Seyfert galaxies, which are kind of intermediate luminosity AGN, and quasars is generally made around a bolometric magnitude of about -21. And quasars, unlike Seyferts, are generally found in massive elliptical galaxies, where it's more common to find Seyferts in disk-type, late-type galaxies than it is to find them to find quasars in those types of galaxies. Now, the quasar itself, obviously, is not the whole galaxy, but a very, very small region in the center of the galaxy, which is about 10 to 10,000 times the Schwarzschild radius of the black hole that's at the center. So basically, that's about a parsec. So that's where all the action is taking place, right in that central parsec of the galaxy. And the current favored lifetime for a quasar is around 10 million to 100 million years, which is actually quite a short period of time. Though it sounds ridiculous to say 100 million years is a short period of time, it is quite a short period of time. So, and another characteristic of these really powerful quasars is they were far more common in the past. The activity peaks around a redshift of 2 and it's been declining ever since. So to get decent samples of these powerful objects, you have to actually look to higher redshifts, and you wouldn't get a decent sample just in the local universe. So, as I've said, all the action takes place in a very, very small region where cold gas is accreting onto the supermassive black hole at the center of the galaxy. Now, in quasars, velocity dispersion measurements of the bulge suggest that the black hole mass has to be at least 10 to the 8 solar masses. Sorry, my little solar mass character went wrong there. And for a typical quasar luminosity of 10 to the 47 ergs per second, that can actually add up to an accretion rate of between 10 and 100 solar masses a year, which really doesn't actually sound like a huge amount when you think of it just in those terms. But when you think of it in terms of the lifetime of the quasar of 10 to 100 million years, that can amount to up to a galaxy's worth of cold gas, which obviously then becomes an issue. Where do you get it all from? So Though I would like to point out that the quasars that I'm looking at in my particular sample aren't accreting at this kind of rate. This is just a real sort of upper limit to powerful quasars. So the problem really becomes, where do you get all the cold gas from to accrete onto this black hole? And even more importantly, how do you actually get it from large radii down onto that central parsec of the black hole? Because it has to shed about 99.9% of its angular momentum to do so. And basically, the reason that we're proposing that it's galaxy mergers that trigger this nuclear activity is that it solves both these problems, in the sense that if at least one of your galaxies is gas-rich, then that solves the problem of where you get a galaxy's worth of gas to accrete onto the black hole. And also, from running this simulation, you can see that as the galaxies pass each other and come back together, you're stretching and varying the gravitational potential, which has the effect of funneling all the material right down into that central region where it can actually be accreted onto the black hole. So if you hypothesize that it is in fact galaxy mergers that are triggering this nuclear activity, then how do you go about checking for it? Well, the obvious way to do it is to look for signs of interactions. Now, simulations such as this one that's running show that interactions between gas-rich galaxies, I think this one shows two gas-rich disks interacting of roughly equal mass. And you can see that massive tails and shells and bands of material are thrown off. And these can be quite extended regions. So the obvious thing to do is to take some images and look for these features. And by that means, try and determine whether the quasar was triggered in an interaction, because these features will last about a gigayear, whereas the quasar, as I said, will last about 100 million years. So you would expect the two to be concurrent. But nothing is ever as simple as it sounds. So here's an example. Now, these two images are both of the same radio quiet galaxy, PHL 909, I think it is. Now, the one on the right was taken with a single orbit HST on the wide field planetary camera. And the one on the left is a much deeper HST image taken with the advanced camera for surveys. Now, there is a difference in contrast between the two images, which is why the field looks slightly different. But McClure, in his study of the morphological rate of disturbance of galaxies, classified this galaxy as undisturbed. Whereas obviously, Bernard, in their morphological study, classified this galaxy as being morphologically disturbed. So basically, what you have to do is make sure that if you want to do these type of studies, your images are deep enough to image what could be very low surface brightness, diffuse features that indicate that there's been a merger. Now, there is also another problem with imaging quasars, and that is the problem of the point source. Because obviously, the whole point of a quasar is that the central source can outshine the entire galaxy, and in quasars it does. So if you're looking to detect very low surface brightness diffuse features, they will be completely washed out by the light from this point source. So here's a sort of further example of this as a problem. Now, here's the HST image that I've just showed on the last slide. And what they've done is they've constructed a best-fitting 2D model with a PSF superimposed on it. They've then subtracted this PSF to have a best-fitting model. And then they've subtracted the best-fitting model from the image. And then, from this image, I'm supposed to use this, aren't I? From this, you're supposed to be able to determine if there's any kind of tidal features or morphological disturbance in the galaxy, which is basically the residuals of this best-fitting model subtracted, this subtracted from this, basically. So that's obviously you know, there's a lot of assumptions in this modelling technique, and you can't be 100% certain that basically what you're getting out is real, or whether it may be an artifact of your model. But fortunately, in 2003, Nadia Szykanska and her colleagues published a catalogue of candidate Type II quasar objects. They selected the objects from the Sloan Digital Sky Survey, and I think originally there was around 300 to 400 of them. And they classified them as possible quasars on the basis of their emission line ratios. And but it's not really an AGN talk without this particular picture. You have to have it, don't you? So just to clarify what a Type II quasar is, in a Type I quasar, which is what previous studies have really focused on, you would be looking down the, where are we? There. The throat of the quasar down here. So you're looking right at that bright region in the center, and therefore it's very difficult to detect these much fainter features. Whereas in Type II quasars, you're looking from here. So that very bright central source is blocked from your view. It's like a natural coronagraph, basically. And it makes it much easier to actually image the host galaxy and detect the low surface brightness features in that host galaxy. And I'll put that down. So basically, we selected a sample from the Type II catalogue of Szykanska, and we basically picked every object that was in the RA range 23 to 10, declinations less than 20 degrees, redshifts between 0.3 and 0.41, and we also made an O3 luminosity cut at 10 to the 35 watts. And that was to ensure that the objects we were looking at really were true, powerful quasars, rather than slipping into safer territories, which may, you know, skew the results. So what we ended up with was a complete sample of 20 Type II quasars, and the sample is unbiased in terms of host galaxy properties in any way. It's simply every quasar that had that luminosity cut in that box, basically. So after all, we then went and imaged our sample. We luckily got the whole sample imaged with the Gemini telescope in Chile. It's 8.1 meter Gemini telescope using the GMOS instrument, which is exactly the same configuration that Christina used for her radio galaxies, which was intentional in the sense that it would make a comparison very direct between the two. So we imaged them all in the R band to get the rest frame optical. Depending on the magnitude of the galaxy, we took between 4 and 9 250-second exposures of each of the objects and co-added them. Now the pixel size of the GMOS detector is 0.146 arc seconds per pixel, which that redshift equates to about 3 to 5 kiloparsecs per pixel. So it's pretty good resolution, really. And we had pretty good average seeing, about 0.8 arc seconds. So, we got good, clear images in which to try and detect these features. So after all that, there's the some of the images, some of the more spectacular images from the sample. Now these all obviously show clear evidence of morphological disturbance. This one here, you've got this amazing long tail and this bridge between the two galaxies. This one at the top is the quasar, and this one here is actually the starburst galaxy. And this one is a personal favourite of mine. We call it the question mark for obvious reasons. And obviously this one is also well on the way to merging. It's this galaxy at the top here is the AGN again. So, and you've also got examples of these shells of material being thrown off, this clumpy, irregular tail down here. Other work by Montserrat Villamartin shows that these two galaxies are actually linked by this bridge. So there's a lot of we see a large variety of features in these galaxies. And interestingly, you also see them at all different stages in the merger. So obviously the activity can be triggered before, during, or after the merger. So there doesn't seem to be, from these images, a preferred stage for it to happen. Well, that was a bit previous, but never mind. So after all that, after we've done our analysis of these galaxies and so on and so forth, what we found was that of the 20 type 2 quasars that we had in the sample, 75% of them show clear evidence of mergers. And 35% of the 20, not of the 75%. So 35% are in the pre-coalescence phase and 40% are in the post-coalescence phase. So obviously, it can happen before or after the merger or during the merger. But on its own, those results don't really tell you anything. They don't really mean anything in isolation. So what we've done is compared them to the results obtained for the Tujansky sample that Christina was working on. And basically, the Tujansky sample is a sample of very, very powerful radio galaxies selected to have radio power on 2.7 gigahertz of Tujansky, steep radio spectra, redshift 0.05 to 0.7. And basically, that gives a sample of 46 powerful radio galaxies. And this is a very well-studied sample, isn't it? It's very, very well-defined sample. Now, we didn't use the entire sample to make the comparison. Our main cut was the redshift. Because our sample is from 0.3 to 0.41, it's not fair to make a comparison between a galaxy at 0.05 and one at 0.04, because you're much more likely to be able to detect faint features in the nearby galaxy than you are in the higher redshift one. So we made a cut at a redshift of 0.2 and used all the galaxies above that had strong lines. So basically, there was one weak line radio galaxy in the sample, which basically means that it's not optically bright. We decided that meant it wasn't a fair comparison because we're looking at very optically powerful quasars, obviously. So we cut that one out as well, and that left us with 21 strong line radio galaxies. Now, as you can see, 95% of those radio galaxies showed signs of mergers or interactions, which seems pretty definitive, really. 50% in the pre-coalescence phase, 45% in the post-coalescence phase. So, I mean, because they're both small samples, you can't really draw a huge conclusion from that, really. I mean, you can't say definitely there's more interaction in the radio galaxy, though it does have to be said it does look that way. Now, this is very interesting because, if we found similar interaction rates in the two samples, that would possibly indicate that the galaxies are triggered in the same way. But the sort of holy grail, of course, is to compare it to a sample of quiescent galaxies, where there is no AGN activity. And luckily, Christina, again, developed a control sample of quiescent elliptical galaxies. And these were selected from the extended growth strip, a deep survey of that. Which survey was it? Sorry? Yeah, part of the deep survey, that's it. So they used Subaru images of that particular survey, and they picked the Subaru images because they have very similar resolution and depth to the images used for the Tujansky sample. Therefore, you could make direct comparisons between the features that you could detect in the two different samples. Now, the original selection of the galaxies from the sample was made by colour, so they applied a colour cut to try and select galaxies on the red sequence. But that doesn't exclusively select galaxies, early type galaxies. So we then visually inspected every single one to try and determine if it was an early type or a late type galaxy. And those that were very obviously disk-like galaxies we discarded from the sample and only maintained the ellipticals and the possible disk galaxies. And the reason we made that cut is because the sample was selected to match the host galaxies of the radio galaxies, and radio galaxies are almost entirely and exclusively found in massive ellipticals. Therefore, that's a fair comparison. So obviously, the host galaxies were also selected to have the same luminosities and the same redshift range as those in the two Jansky sample. Now, because of the similarity between the host galaxies of the radio galaxies and the two type 2 quasars, we actually didn't have to apply any kind of luminosity cuts or anything. And to that sample, the only cuts we applied were that we only used the control sample galaxies that were actually in the same redshift range from 0.3 to 0.41, just to make the resolution absolutely directly comparable. And it also left us with a big enough sample to actually make a comparison. So what we ended up with was a sample of 37 quiescent early type galaxies, of which 68% show signs of mergers, 27% are in the pre-coalescence phase, and 31% in the post-coalescence phase of the merger. So looking at that, you think, no, there's no difference between the two. There really is no statistical difference between the two. So if we're on those grounds, think, no, that's not it. But then we also measured the surface brightness of the features in all the detected features in the galaxies. And so here's a comparison between the features that we measured in the type 2 quasars. So this shows the surface brightness against the number of features. So as you can see, for the type 2 quasars and the two Jansky strong line radio galaxies, it's pretty much identical median value, pretty much identical range of values for the surface brightness. However, when we actually compare the type 2 quasars to the control sample, you can immediately see, without really any closer inspection, that there's a huge offset between the surface brightness of the features in the type 2 quasars as there are in the control sample, with the control sample having a median value almost a magnitude less than the control sample and a range up to 2 magnitudes less. So the features in the control sample are actually much dimmer on average than they are in the type 2 quasars. Pardon? It's R band, R prime. Yeah, R prime, yeah. So, what is a feature? Yeah. So, oh, that wasn't meant to happen. So when we're talking about measuring the surface brightness, you would measure the surface brightness of this tail or this fan here, this shell here, this fan here, this bridge. So you're talking about measuring the surface brightness of these features, basically. That's what I'm talking about when I say measuring the surface brightness. So let's see where we get. So yeah, immediately your first thought would be, it's emission line contamination. And what I mean by emission line contamination is that in the AGN, there's obviously a very powerful illuminating source in the center. I mean, that's what an AGN is. So what the idea of emission line contamination is that the features in the quasars and the radio galaxies are unfairly brightened by scattered light from the AGN, not from any sort of parameters of the merger itself. So the gas and dust would be present in the quiescent galaxies as well. It's just not being illuminated by this huge, powerful source. So, but luckily, we're in a position to check whether that's the case or not. So, of the 20 type 2 quasars, of the 20 type 2 quasars, that we have images for, we also have Gemini long-slit spectra for. And the 10 of those have passed through at least one of the features, the detected features. And for 90%, the galaxies have at least one feature that is continuum dominated. And for the 2 Jansky radio sample, they had 22 long-slit spectra that passed through at least one of the features in the galaxy. And of those, 91% had at least one continuum-dominated feature, which indicates that emission line contamination is not a huge problem in either sample. It's, it is going to play some part, but not a huge part. So what are the reasons then for the features to be brighter? Now, one possible reason, and probably a very likely factor, is that the progenitors of the mergers are different, in the sense that the progenitors merging into the type 2 quasars and the radio galaxies are likely to at least one of them be gas-rich, late type galaxy, which produces a brighter starburst, more prominent features, basically. And you're looking at probably an equal mass merger. Whereas in the quiescent galaxies, where we see features that are on average fainter, it's likely that it's what you would call a dry merger, where it's a merger between 2 elliptical galaxies and there's very little gas or dust available, and therefore you don't really see the features are not as bright and they fade quicker, basically. So, but there is another possible explanation, and that is that there's only a certain period around the coalescence of the black hole where the AGN can be triggered, because by saying we're assuming in the quiescent galaxies that they never have been an AGN and they never will be an AGN. But as I said, I mean, the AGN lifetime compared to how long the features are visible is a very small fraction of that. So there's no real way to test whether it has in the past been an AGN that I can think of, or, it won't at some point in the future be an AGN. So this is only a possible scenario, is that the AGN activity can only be triggered doesn't like that one. Triggered and sustained here around the peak of the merger when the features are at their brightest. And by the time the features begin to fade and fall below the detection limit of your images, the AGN's long since passed, and all you're looking at is the fading tidal remnants of the merger. Now, one way to test for this is that the peak of star formation and the peak of black hole accretion kind of occur around the same time. There's a slight offset, as you can see from this. This one's black hole, this one on the bottom is black hole accretion rate, this one at the top is star formation rate. And this pertains to the merger between 2 gas-rich galaxies, I believe. So you can see that they occur at roughly the same time. So if you can in some way date that starburst population that's or pretty much always occurs with a gas-rich merger at the same time, that could tell us when the black holes coalesced, and therefore how offset the AGN activity is from the coalescence of the black holes. Now, as I said before, we do have Gemini long-slit spectra for the vast majority of the galaxies in our sample. We're hoping to be able to finish the sample with long-slit spectra. So we're planning on doing spectral synthesis of the stellar populations in order to try and date them and see if this theory holds any water. So basically, what I talked about so far is the disturbed galaxies, as if they're the only ones. But there are, in the sample, 25% of the galaxies are undisturbed. And I should not play with technology. Just put it down. Step away. Okay. And I mean, these are I wasn't even touching it then. Right. These are all the undisturbed galaxies in the sample. As you can see, the one in the middle there is an undisturbed disk, which is, as I said, quite unusual for powerful quasars. But the other four are all actually quite spatially compact and interesting in their own way for that reason. And hopefully, with our long slit spectra, we'll be able to make some determinations about their stellar populations and what's going on there, because what this proves is though mergers may have some influence in triggering powerful AGN, it's not the only factor. There has to be other ways of doing it, otherwise these objects wouldn't exist. So though it's part of the picture, I don't think it's the whole picture. So to summarise, we find the same rate of morphological disturbance in both type 2 quasars and quiescent elliptical galaxies. There's a higher rate, apparently, of morphological disturbance in the powerful radio galaxies than in type 2 quasars, but the surface brightness of the features in both the type 2 quasars and the powerful radio galaxies are up to 2 magnitudes brighter than the quiescent ellipticals. Okay.
All right, thank you, Patricia, for the talk. If there are any questions?
I have not got a clear opinion about your results, but however, I have in mind some literature different from yours, in which they get some results quite opposite, that they do some statistics and they find that there is no correlation between merging and the quasars. And also, it is well known that the quasars are more common in isolated regions rather than in clusters of galaxies. So I don't know whether there is some discussion about different groups.
Oh, yeah, massively, yes. Yeah. There's a lot of different literature. Oh, sorry. There's a lot of literature that contradicts one another in their findings. And a lot of these contradictions can come down to the way samples are selected, in the fact that, I mean, it's quite accepted now that it's probably in lower luminosity objects, mergers probably don't play such a significant role. I'm really only talking about very, very powerful quasars here. So that's, you know, that can confuse results. Also, what I was talking about, the imaging, you know, if you use shallow imaging, like I've read papers where people have used sort of shallow surveys to try and detect morphological disturbance, which is going to skew your results away from mergers, because, you know, you're not going to see those kinds of a lot of these features are very faint. I mean, I think we measured down to about about 26 or 26, 27. So a lot of these features are very, very faint. So that can also skew the results. So, it's still a question that's up in the air, you know, and I don't think my results here actually, you know, say it's one thing or the other. I think they're very consistent with the idea that mergers are a factor in triggering quasars, but they're certainly not the only factor, I don't think.
Well, actually, and I may say before, sorry, that about the environment also plays a role, definitely. And actually, this is the next step we are going to take, because these GMOS images are really big. They are like 5 arc minutes per 5 arc minutes. So we are going to characterize environments and try to see what is the influence that have in the triggering of the AGN. And what Patricia said, there is a lot of controversy, and basically we pretty much agree that, within all the people that is working in this, that they have a luminosity issue. No? High luminosity AGN look like they need something major, like a merger, an interaction to be triggered, and low luminosity AGN, like CFIRS, for example, only require a secular, like Babar or something, or this instability or something like that. And to make a bit of propaganda, Clive and I, we are starting organizing a conference on AGN triggering mechanisms for next year. So, not sure, maybe in Leiden, in Holland, but here is another possibility. So I encourage you to go and enjoy the discussion. That will be. Any more questions? Sorry.
Can we learn anything about the nearby quasars, if there are very few? But can we learn anything about their origin, because we can see the images much better? And on the other side, some merger galaxies, like the Antenna group, for instance, are producing any kind of activity?
I don't know the answer to the second question. We are looking at individual galaxies here, but we're presuming that you can extrapolate the results of, you know, higher redshift galaxies to the local universe. Basically, if you know, we're assuming that if we find that it's triggering at higher redshift, mergers that trigger it at higher redshift, then those factors are still going to be the same at lower redshift, basically, in the local universe.
And by the way, which is the closest quasar we know? The redshift. Does anybody know?
What, of this luminosity? I actually don't know the answer to that. Anyone? No.
Cipher are very local, but quasar, like a powerful quasar, I don't know, maybe 0.01 or 2, something like that. But in the local universe, you find ciphers, but not radio galaxies or quasars.
Unfortunately, I missed the beginning of your talk, so I'm not sure about the selection that you have done. But if this is a complete sample in any sense, and what you have suggested is that you are observing somehow two different evolutionary states, it would be straightforward to you to test that just simply counting objects, no? If you have a volume limited sample, and then you can say, okay, what is the probability? This is the number of objects that I observe in the quasar phase, and this is the amount of time that I'm able to see the feature.
Yeah.
You would be able to test immediately whether your model is right or not, because you would expect the number of objects in the second phase according to the different times of intervals.
Yeah. I mean, there is a whole sort of timescale argument there, and we have actually performed that sort of calculation where you expect the features to be visible for a giga-year, and you expect the quasar to be that's not the one. That's it, right? So basically our sample is complete. It's just, and but yeah, as I was saying, we have considered that, you know, if you expect the features to be visible for a giga-year and the quasar to be active for a maximum of 100 mega-years, you expect to see a certain proportion of disturbed galaxies as quasars. But what we did actually find was that rate was, what we actually found was lower than you would expect if you assume that every interacting galaxy goes through a quasar phase. So, but then it's a very naive assumption that they'll all go through a quasar phase, because there's so many different parameters involved, like the amount of gas available and all that sort of thing. So it doesn't really account for all those things. It's very difficult to know how to account for those kind of things, really. So yeah, it is kind of there's so many variables that it becomes quite difficult to do, I think. Hello.
I have a suggestion, maybe not or to Jansky's and on your sample. It's not only the amount of gas in the galaxy, but also the size. Because if it's a minor merger rather than a major merger, perhaps it couldn't trigger the AGN. So that may be one thing. And the other thing is studies can be done at high redshifts.
Yes, yeah.
Because, you know, there's this idea of cool flows by Deckel and all these people. And they're also claiming that these cool flows, I have in mind, my idea is that only if you accrete gas, you know, quickly and in a violent way, you could trigger an AGN. But if you go to higher redshifts and you find much less merger features, maybe that could be in favor of these cool flows. We could be a major step, actually.
Yeah, except for the fact that quasars don't tend to be found in dense clusters, because cooling flows tend to be onto the central galaxy of a cluster, don't they? I'm right there, yeah. So that isn't really the environment you'd expect to see quasars in. I think that's more radio galaxies, because postulating that for weak-line radio galaxies, aren't you? So yeah, I mean, it's definitely a possibility. But I think the reason that the detection of features at higher redshift is less is because it's just more difficult to detect them. So, you know, yeah, so I mean, because people try and use other techniques rather than visual classification, as we've done, where they, like the CAS parameters, where they look for asymmetry and clumpiness, and I forget what the other one is. Yeah, that one. Yeah, concentration, yeah. So, but funnily enough, Christina tried to use that for the control sample, not the CAS parameters, but the other T parameter. Was it Van Dockum or? Yeah. But what I was going to say is that I mean we did it all by visual classification. That wasn't just in my head. No. Well, the tidal parameter, that's the one, yeah. And what she found was that galaxies that it classified as undisturbed, when you eyeball them, they are obviously morphologically disturbed. So it's very difficult to know actually how to do it, because at higher redshift, as I say, detecting morphological features by eye is very, very difficult, but not sure how accurate these parameters actually are. So, yeah.
Questions, Cassiana?
Sorry, this is a simple.
I like them.
I know nothing about this topic, but I am not surprised that some of these quasars are the result from an interaction, a fusion or whatever, of two galaxies. I'm surprised by the fact that you are able to see this. I mean, because the quasar is a very massive thing. The spot you have shown is a very big thing.
Yeah.
And you are detecting these features, which are like arms or loops or whatever, which are very far away, the center. And the merger process takes a while, which is not that long. And all these remaining things in a not so long. If you could nearby example of a merger, and you could put a spot like this, like the size of your quasar, how many of these merger features would you be able to see?
That was a simple one. Honestly, I don't know. I don't know the answer to that. So, sorry, what you're saying is, if I looked at quasars in the nearby universe, yeah, in the
how many features?
But do you mean like a mask or something, like a coronagraph or something like that?
In the local universe? I honestly. Yeah.
No, she's talking about putting a mask in front or something like that to detect the extended stuff. But the thing is that she's using like kind of a natural mask because she's selecting type 2 quasars. So the torus is acting like a mask for the AGN. So that's why we are able to detect the feature even in the case of quasars. In type 1 quasar, you have to do Galfit or something like that to extract the PSF, as she shows at the beginning, to be able to see something, no? And
yeah. But I mean, I agree with you. It is amazing that you can see all these things at this redshift. But I mean, they are very deep images, so you know, with fairly good resolution. So
not only because of the redshift, because of these are prominent features which are quite far from the center of the merger issue.
Yeah, quite extended.
Yes, and this is something which I suppose that in mergers, when they evolve, these extended features don't last so much.
I think that they tend to fade at the same rate as the closer in features. I think it all fades down at kind of a very similar rate, even the long extended features. However, I suppose that if you have a very long tail or as in, oh no, going the wrong way. As in this one here. Oh. As in this one here. It's not just, you don't just have to worry about the fading, but dispersing and becoming far too diffuse to be detected. Yeah, there is that issue. So, but I have to say that if there were enough of these in the local universe to actually construct any kind of sample out of, I don't really know what the difference in the feature. I mean, obviously you'd be able to detect fainter features on smaller scales, maybe, but I don't really know.
Any other?
Well, it was a good short talk, so have to make up the time somehow.
Not short.
Good short, correctly short. That's what I mean. It was meant to be praise, not blame. You see, the statistics seem to suggest that the radio loud and the ordinary strong optical quasars and the non-active things all have about the same fraction of mergence. Mm-hmm. So obviously the problem really seems to be not how a quasar is triggered, but why are some objects not quasars? Yes. Isn't that the real problem?
That's also an issue. But as I mean, yes, that is a very, very interesting question. And I think part of it can be answered by the types of galaxies that are merging. I mean, if you get two ellipticals merging, then there's not enough gas really to produce a bright quasar or radio galaxy. I mean, you may get some low luminosity action, but nothing that bright. And also the time scale is another issue, because as I said, we're presuming that these galaxies have never been quasars. But why would we presume this? I mean, they all will never be quasars. They may be pre-quasar or post-quasar. So, I mean, that's also another option.
So the answer is more statistics, right?
Yeah, more work for me.
But the answer is statistics, but also, I mean, we don't want to give the impression that we are finding the same number of interacting systems in the control sample and in the AGN sample. In fact, one thing that Patricia hasn't mentioned is that if she does the cut in surface brightness, if she compares only the features that are as bright as the ones that we are detecting in the AGN sample, the percentage of disturbance that she gets in the control sample of quiescent ellipticals is considerably lower than the one we measure for the AGN, especially in the case of the radio galaxy. Yeah.
Yeah. But I mean, it's much more. I mean, here I've only compared the comparison between the control sample and the radio galaxies isn't really a good one here, and I'm not really trying to compare the two directly, just intermediately through the type 2s, because Christina found that for her strong line radio galaxies, 95% show signs of interaction. But when she utilizes her full control sample from 0.2 to 0.7 to compare it to, you actually only find 52%. So it's much more pronounced between the radio galaxies and the